Hello, this is Richard Collins. I'm looking at a project that I did back in 2013 where I reviewed seismometers, particularly broadband seismometers, to see if they would be useful as gravimeters, particularly 3-axis gravimeters. The sensitivity of some of the seismometers is such that they can see the what I call the sun-moon signal. And let me see if I can find it. Some you can see they're kind of the red in here. If you can see it in there, is the sun-moon, what I call the sun-moon signal or lunar solar signal, the gravity signal at the Earth because of the sun and the moon, or at an Earth station because of the sun and the moon. And these seismometers, we're looking at the vertical, the Z component of it, and most of them are rather noisy, as you've seen so far. And here there are some where there's a similarity, at least in broad outline, between the seismometer signal and the gravity signal. Now, the gravity signal is in absolute units. These are nanometers per second squared. The residual, after you take the sun at the station, subtract off the sun at the center of the Earth, the moon at the station minus the moon at the center of the Earth, and do all that vectorially, dotted into the local, in this case this is Z, dotted into the local vertical unit vector, and you get a scalar, which is the magnitude of the signal that you should expect. And while these aren't really great fits, it's actually kind of amazing that you can do this at all, considering that the seismometers weren't supposed to do that. Now, I would like to make a point here that even this one, which is probably off in the amplitude, the offset in here is the correct offset. So now, I don't know if these signals are normalized, in some fashion anyhow, but there is, how to call it, the units that are shown here are the correct units if you're going to read gravity, or actually, what is gravity but acceleration? So it's just a different type of acceleration measure. And we call it gravity when the acceleration comes from the sun and the moon, for instance. We call it acceleration when somebody hits you or you have an earthquake. Anyway, this is what I was facing after considerable effort, to get to where I could pull these signals out and compare them. So these are all samples of seismometer readings, the scale here. Oh, these are 1 month. Basically, these are 1 month at a time for each of these stations. So these are the vertical signal from some seismometer. Now here, I did find some of these, and this one is GATD, the G network, which I'm sorry, at the moment I forgot which one that was. ATD, a station there, and then the Z component. This was from 2013, the first month, first day, to the 31st day of the year, so January, during that year. Now, it might not be obvious, but I've done a couple of things in here. First of all, the seismometer is reading velocity, so I had to differentiate the signal to generate an acceleration. Then, in this case, the acceleration calculated that way from the signal is a simple linear relation that is an offset and a multiplier to the gravity signal. So this is a station, G.ATD, a broadband seismometer that can be calibrated as a gravimeter. I'm not sure what happened in the north and east components of the seismometer. A lot of these, the seismometers are 3-axis seismometers. So let's move on. So G.ATD would be a good one to include. So out of many stations, there are some that can be. Even these, well, you would say, oh, that's so doggone noisy, I don't know what to do with it. If it's scaled properly, even with the noise, it gives you some constraint on the gravity being received at that location. You actually know when things are happening, even if they're not happening exactly as the signal should indicate. So there's more going on than just the gravity, the sun-moon gravity signal there. So this is G.FDF, G.HTC. There's several G network seismometers that work very well in the Z. So I'm just kind of HTC, INU. Here's one, KIP, G.KIP. That was it. Yep. So anyway, this is kind of the process. After I got the basics of it working, I had to sort of manually or visually screen a lot of these. Eventually, I learned to clip this and get it to where I can run regressions through here, and then I can pick out which ones work better. Some of these I think are tilted. Some of them I think are turned around the east, and around the vertical axis that is not pointing north, for instance. I don't know. It wasn't easy for me to try to figure out why. This is G.PPTF. Again, G.PPTF. Yes, that one. Now here, this is the periodicity and the direction. So when the station signal is going down, the gravity was going down. When the station's signal went up, the gravity went up, or vice versa. When the gravity signal went up, the station went up. So the station is detecting the sun-moon signal. That wasn't its intended purpose, and I think they cranked up the amplitude so they get more signal. I hope I'm not saying anything bad about anybody, or again, this is not the purpose of the seismometer network. This is G.RER, and why some of these, you see the gravity signal seems to come here. I think that's a tilt. I'm almost certain that there. I don't know. I wanted to go in and either get some ground truth and find out which direction these things were facing in, or run some massive statistics to back solve and find the best orientation for this thing. So that actually is not a bad strategy in some cases. You take a 3-axis seismometer, you throw it out on the field some way, and you start recording it. If it's supposed to be sensitive enough to the sun-moon signal, you calibrate it against the sun-moon signal again and again and again and again for every possible orientation you can imagine until you find the best fit. And that presumably would tell you, oh, this is north, this is the vertical direction, this is the north direction, that's the east direction at this location. And the location is specifically so-and-so, because, for instance, if this drifts, if the longitude was off, then these timings would be off. If the latitude was off, then I presume, yes, probably the height of this would change. So you got a number of things that you could do, but there's so much data in here. You have a station that sits and does nothing but generate, maybe 100 numbers per second in each of the vertical north and east channels, and no one hardly ever looks at it. In the quiet times, and they say, oh, that's just the sun-moon signal. We don't need that. That doesn't tell us anything about, earthquakes. So, it's not any use to us. Well, in fact, all of the quiet times for, if they're calibrated and actually tuned a little bit. I mean, if stations went to the trouble to go in and make this fit even better for the quiet times, then they would have basically a 3-axis gravimeter and a seismometer all in one. The gravimeter can be used in a global and area networks for imaging purposes. Then I think the seismometer data makes more sense. All right, let me just quickly flip through here. What was that one? I like it when they fit fairly closely. Again, I don't know. Now, I did a lot of research on the station or the instrument response, and it could be that in some of these, what I'm seeing is a nonlinearity in the instrument response. I don't know. I don't know why some of these act. Oh, I know possibly what's going on. Some of these stations are G.TAM. I have no idea. Some of the stations were near the ocean, and besides the earth tides, there were also ocean tides, and I think I saw quite a bit of that. It's hard for me to summarize, I don't know, maybe a year's worth of work in just a few minutes. Let me see. I'm going to just close this. So that's some of the images in here. That's just a sampling of things that I kept. The east-north studies were interesting. Remember that BKMCCM, I think that was in there? This one, I think, is not aligned quite properly on the north axis. I'm not quite sure. You wouldn't want to use a magnetic north, but rather I wanted to say geodetic north, something that dealt with the figure there. So a lot of these are close. There's some similarity between the expected gravity signal at that location and the quiet time response or signal from the instrument. But this is about as close as I got most of the time. There's some are very close. Others are not. You see, I can't. Let's see if do I have a way to blow this up? You see, little things like this always made me curious. What was going on there? Now it's possible I have an error still. I have no station for which I had cooperation, so I have no station where I knew exactly how something was oriented, and anyway, I think it's possible there was an error in the way I calculate the east and north components of the signal. That was part of why I was trying to do this. I was trying to use these really messy and noisy seismic signals as a way to verify that the east and north signals at gravimeter stations, or what I was hoping were gravimeter stations, matched the theory. The theory says here's a vector of gravity at the station, and these are its components. That's just Newtonian GMM over r squared. The only let's see if I can do. Oh, I'm going to switch gears here for a minute. Let's see. I think here. Yes, to give you an idea, this station. I had to merge a lot of different ones. But again, this gives you a rough idea of the number. This is about 10,000 instruments. Instruments, in this case, channels, east, north, and vertical for this location. So roughly 3,000 station locations and various instruments. And what I was trying to do here was to figure out which of these were giving the best results. So let's see. The transportable array, I zoomed by it. TA, I recognize that one. There's actually some instruments there that give good results. What I was looking for, GE, I thought, this must not include the G one. Let me try another. Let's see, here's the largest one. Stations, okay. But I was using this when I was running the regression, so I had to look up the station properties. So this is the file that I produced or manually built to do it, and it gives the name of the network and so on. So this one, these are transport. Oh, G. HDC. And I think that was one of them. I'll have to go back. I'm getting distracted because I'm remembering so many of the questions I had about trying to locate. So there were some of the stations that were in quiet places, well maintained, installed well, the proper type of instrument. And they could be used as 3-axis gravimeters, or at least in 90% of the time, certain instruments types can be used for vertical gravimetry. There's a few that are where they took the time, and they're also good for the for 3-axis gravimetry. Not save it. I'm trying to leave these in their original form once I do this. So that's kind of the state of affairs there. You see this little note in here. It's hard to see maybe for you, but it says velocity, and I'm reminded to have humility, because for the longest time I didn't know. I made the mistake of trying to compare the velocity to the acceleration, and I kept saying, why am I not getting results? And because I didn't know what the signal was. I thought they were all accelerometers in there, and it took me the longest time to be sure that they're. When you just grab data and start looking at it, it's not always. It takes a while to find the documentation on it. Figure out what the units mean, and so on. So that's just left in there to remind me to have humility and never take anything for granted. There's not much in the I'm going to stop here. This was the seismometer review. I was almost going to get off onto the gravimeters. So close this. Okay. Thank you.